Welcome to another edition of Science Like Me. I'm your host, Sara Naderi, and I have the pleasure of interviewing Tara Javidi today. Tara received her BS in Electrical Engineering at Sharif University of Technology in Tehran, Iran. She received her MS degrees in Electrical Engineering and Systems and in Applied Mathematics and Stochastic Analysis from the University of Michigan, where she ultimately received her PhD in Electrical Engineering and Computer Science in 2002. From 2002 to 2004, she was an assistant professor at the Electrical Engineering Department at University of Washington. In 2005, she joined the University of California, San Diego, where she is currently a Jacobs Family Scholar, Halogeolu Data Science Fellow, and Professor of Electrical and Computer Engineering. Tara is a prolific researcher and academic leader. In particular, she is a co-principal investigator at the Institute for Learning-Enabled Optimization at Scale, also known as TILOS, one of the prestigious national AI institutes enabling longer-term research and U.S. leadership in AI. Tara's research interests are in theory of active machine learning, information theory, and optimization in face of uncertainty. She is particularly interested in applications of ideas in these fields to engineer better, faster, and more ubiquitous wireless communication networks. Tara is currently the editor-in-chief of IEEE Journal in Selected Areas in Information Theory. She is also passionate about and very active in advancing diversity, equity, and inclusion at the institutions of higher education, as well as in the engineering profession. Welcome, Tara.
Thank you. Thank you for having me.
Yeah, of course. So tell me more about your research. What gets you excited about what you do?
In general, what I'm really excited is the use of mathematical modeling and abstraction of ideas and then translating them into engineering specific solutions. So that's sort of the general excitement, but it varies from year to year depending on where we are with technology and new ideas coming out. So these days I'm really excited about using ideas from AI to actually optimize large-scale engineering systems, in particular wireless communication networks, as you mentioned, but also large-scale systems for monitoring, say robots that go around and do monitoring, looking for anomalies, environmental monitoring, and questions of this sort. So that's sort of the big picture. But
can you tell me more about how you use AI in wireless communications? Like what kind of data are you looking at that needs that kind of processing?
Yeah. So let's speak about, let's say, the wireless communication infrastructure we have on campus, right? So we have all these access points that work for all of us to get connected. In classrooms, we are now using them. The students are connected. So you can sort of ask yourself, what are these technologies? How are they working? Historically, we developed these as small-scale solutions. So, for example, Wi-Fi technology, everybody has a Wi-Fi access point these days at their home. This was a small-scale engineering solution for 4 or 5 people at home to communicate. Now we have scaled it to be serving tens of thousands of students on campus. Let's say a class ends, they all leave the class. There's 100 students in my class. They're all leaving at the same time. So there are new challenges that this technology was developed for far smaller scales. And now we are deploying it to serve large numbers. So the question becomes, can we actually use methods from AI to sort of recover peculiarities that we didn't think in the design space? Our models were insufficient to think about them, or in case of Wi-Fi, the technology grew out of a smaller scale technology. So that's where broadly we look at. The data the data is everywhere. But you nailed the question the right way. For engineering solution, the data is not abundantly spread over the internet the same way that first-generation AI models really benefited from data that was available and publicly available text and image data, for example, on the internet. So in engineering, data is really the gold question for us, and that's where this idea of active AI or active information becomes an issue, because now I have to really ask myself, what data should I collect to be able to answer better questions? So for example, as part of TLOS, we ask what data is critical to make sure that my Wi-Fi access points are optimized in ways that when the class ends and everybody's moving, the traffic is handed off correctly. Now, this example is for access points in a campus-wide, but you can imagine that this is what operators do with cellular control of cellular towers that act like access points, and all other type of satellite communications and whatnot. So that's where I'm really focusing on.
So I'm trying to understand, usually it's easier to process data that's already been labeled and you have some idea of what it means, but I'm imagining with this, it might not necessarily be labeled data. You're just getting like a stream of signals and having to find patterns in that.
Yes, but some of our signals are kind of labeled. So for example, when you collect power, when you collect outage events, they're kind of labeling that the network didn't work very well. My power consumption of this device was very high, it heated up. So some of the data itself acts like signals that normally in a classic AI system would be called a label, as a cat or dog. In engineering solution, that's where the benefit is. Some of our labels are really embedded in the performance of our networks, and our systems are designed to sort of more or less keep track of these in order to do all sorts of diagnostics and so on. So we use that information quite a bit.
Nice. What about, I realize that your background is also in stochastic analysis, which I would imagine maybe, which just so we share with the audience what that means, it's like when you can't predict something, right?
Yeah.
So have you found it that when you're trying to optimize these systems, is it ever predictable, or is there some sort of like eventually there's some predictability about it? Or
that's a great question. So classically, stochastic optimization came out of this idea that we want to optimize systems or we want to control systems, but there are certain events that we know it's futile to really predict them precisely. And wireless is a prime example. Depending on any room and the layout of the furniture and the frequency of the signals, how this signal gets to you is not going to be predictable. If I want to predict it, it's very expensive. So classically, we would build mathematical models that would summarize this unpredictable behavior. So the behavior itself unpredictable, but I can summarize the statistical profile of how to think of it. Think about like any kind of game that you play, you throw a dice, the outcome is unpredictable, but okay, equal probability any of these numbers will come out. So classically, we did a lot of modeling in stochastic, we did a lot of modeling to enable stochastic optimizations. It built on models that we would go out and make measurements and build these statistical models for physical reality. So as you can imagine, those models are not full bulletproof, right? So they are made as much as the data is telling you. So this is another place where AI can really come to help us really replace those models with more sophisticated summaries of the data that is happening. So that's where sort of a really nice connection between AI-enabled methods replacing those classic old models that we have developed for simplicity to get our analysis to work.
What if you can wave a magic wand and get more data about the environment in which these signals are traveling through, if you will, what would that look like? For example, you had mentioned the furniture in the room could actually affect a signal and how it's traveling. If you had computer vision as part of another layer of data about the environment, or I don't even know, sound. What if you could just be like, I can get all the information I want? What would that be to make it easier for you to make the predictions?
To make better AI models that
right.
predict the mobility. Yeah, so we have something called data processing inequality. The more data, the better. Technically, the more information we have about the environment, the model will be more precise. But now here is a bit of a trade-off. I can make a really predictable model that does a really good job with this one room, but I would like it to be somewhat transferable. So when I go in a different room, it doesn't completely get stuck in the previous room's configuration. So you have this trade-off between transferability and generalizability of your model and capturing some aspect, temporal aspects and spatial aspects of this room that you would like to learn. And our models try to do both. There are some coefficients that we keep them for longer. They would transfer the structure or the physics of the problem isn't changing from this room to another. And then the layout of the furniture and the images and those things have to be translated into short-term information as well as long-term information.
So I would imagine, okay, I'm just starting to like use like fantasy kind of thinking here. But like if you had like a quantum computer and you could just process any amount of information instantly, if you were to just be able to always know what the environment looks like, and I don't know, you know the weather, you know how many people are there, you know how they're moving around, you know all of that, would that be the most optimized way of being able to move around mobility? I don't know. I'm sorry. I don't know if I'm going way off topic.
No. This is a very good question. Bottom line, if everything is predictable, I wouldn't need to actually even predict, right?
Okay.
So if I go so far, the interesting thing is people are moving in unpredictable ways. And so, yes, if I could learn everything that is predictable out, and I would just be left with the inherent uncertainty in the system, which is who will stay in this room and who will leave, right? Like if that's just like, think about it as like a simple binary decision for every person within the next minute, that will boil down, my model has to just capture those binary variables and sort of make a bet over them. And then as we all move, the cameras, and also I have to say the wireless signals can be acting like, because of what I said, it's the signature of the environment. It's also a way of creating images. That's how radar works, right? So it's in different frequency bands. So that's what it really is telling you. After people have moved, you have disambiguated, for a better word, or you kill the uncertainty of what everyone's intention was. They have either moved or stayed, right? So in that sense.
So let's move towards a little bit more about TLOs. I know that TLOs, there's specific practical applications in networks, which is what you lead, and right?
Yes.
Okay, and then robotics and chips. And then there's foundations, which I've always described, and correct me if I'm wrong, those three ones are the practical use cases of trying to optimize, and then foundations is almost as if they extract what they've mathematically learned and maybe can apply them in other arenas. Would that be a right way of?
Yeah, absolutely. So when we proposed the idea of TLOS as an AI Institute proposal, that was exactly what we thought. We thought the theme is doing optimization at a scale that fits the needs of new applications. Robotics, communication networks, and chips all have two aspects in common. They're all very much attached to the physical reality that they operate on. So there's physics attached to it. Their data is not completely arbitrary. And the second thing, their scales have grown to be so much larger than our, traditional conventional optimization methods could handle, that there was sort of a gap between how these systems are optimized and what these optimization techniques were capable of handling. So we had to do a lot of heuristic, we had to do a lot of engineering, sort of a suboptimal decision making to solve them. So the three use cases are very much, and in fact I would argue these are three use cases that, because of the sheer need, engineers have almost naturally gone ahead and come up with heuristics or methods to optimize them that can also lead back to maybe show the way in terms of what kind of underlying architecture the systems have that allow these optimization methods that engineers have called heuristic to work well for those applications. So there's sort of a three-way going. First of all, using AI to do optimization in places that it has not been able to succeed, and then use cases feeding back and say, we need more, we need more. So it's sort of, and this is what engineers are doing, or this is humans when, for example, in networks, we talked about Wi-Fi access points. There are a lot of engineering intuition that goes behind the IT team that goes and deploy these things. And so we can really learn from, that intelligence as well. So, yeah.
Are there times when you've learned the methods in which somebody tries to deploy AI optimization in chips or robotics and applied that to networks? Does that scenario happen, or?
Yeah, that definitely. So, for example, I have collaborated with my colleague Farinas Kushanfar, who was really interested in how we actually basically map really expensive AI solutions onto the hardware. So we call it machine learning, but we often kind of don't care that it's done on a machine. In reality, compute has to be mapped to different segments of your machine in terms of memory use, compute use, GPU use, and so on. So she was really interested in optimizing the performance of the hardware for this kind of AI task that they were doing. And so we used an optimization technique that I immediately thought, oh wow, if we can really map out compute in this way to different components, could sort of take that same idea, and now you think of a large-scale network with wireless devices, there is sort of a similarities in when they are computing, they're thinking about a computational graph being mapped out to resources that are physically there and on a device. And the same thing applies here. I have compute different access points with different compute power, with different, even energy budget and so on and so forth. And how can I lay out my infrastructure or my access point associations with the mobile devices to do this job better? So that was sort of more or less immediate, and that's what we are doing. Yeah.
I realized usually I ask like where your research applies to the real world in terms of like how it's practical, but I feel like with yours it seems pretty straightforward. You're basically making better wireless networks so that people can use their cell phones or Wi-Fi wherever they are without having any kind of dips in connectivity and things like that.
Yeah. So, in general, I have been always very much interested in the application of, I've been kind of really amazed at our human ability to think about abstract ideas that are general and then systematically walk through that reasoning and then translate it into a system that does the job that we want it to do. So while in Telos I'm really focused on wireless communication, that's not the only use case that I'm really interested. For example, I'm really interested in the use of orchestration of resources in terms of collecting information that can arise in robotics application. A few years back, I decided a very good example, and this is equally, sort of easy to explain to students, especially undergraduate students, is use of information in navigation and monitoring. So let's say you have cameras in your home. Let's say I get the next generation, they'd be on drones or they'd be on ground robots. And now I travel a lot and I get false alarms a lot from the security system. Now, imagine that if I use cleverly what each camera is seeing, and now I have the ability to move them. It gives me a lot more fine resolution information about what is going on inside the house. My house is like 2 floors, stairs, and as usual, it's not structured in a way that with one camera you can see everything. But now if I have movable cameras, a similar question comes in: which information I should collect, that from where, depending on maybe there was a noise, maybe a noise sensor started the alarm, like maybe I should try to find that source. So that has been like in my lab, there are undergraduate students who code simple to use robots to respond to things like this. I lost my keys. Can I actually sort of think about the last time I saw them, and then have the small drone kind of fly around and make a noise when it finds it? Now with the find like these air tags or something, that project is a bit of an overkill, but still is an interesting question that the students find very interesting use cases for. So yeah,
I think that's really cool. I think sometimes people that are using these systems, whether they're cell phones or looking at their security cameras at home, take it for granted the research that goes behind to make them happen in such an easy way for consumers, right? And I love, like, you know, I don't know, thank you for doing that kind of work so that we can have these kinds of luxuries in our life to be able to do it.
It's also very fun.
That's cool.
I invite everybody to think about whatever is around them, how would they structure it differently. That's already kind of thinking about engineering, and then think about it, can I think about it in a very general abstract way so that I can carry it from wireless communication to robotics information, right? So that's really fun.
So we're going to rewind and understand who little Tara was. So I like to think about, like, you know, first, like when you were in middle and high school, did you always know you wanted to become an engineer, or was there like a experience that you had as a kid that made you feel like, oh, this is really cool?
I definitely was a geek with all the standard definitions. I remember I was very entertained by a toy that I have built that I forced all my cousins to play with. I don't know if they liked it, which was this wire that was shaped very strangely, and you had to pass the loop, you know? Have you seen it? It's like Parks or something.
Okay.
And if it touched, it would, you know, turn a light on, and they would
cool.
lose, and they had to do the same thing. Yeah, it's a very simple electric circuit that closes when the loop and the wire hit. So I remember I was very much more amused playing with this toy than any other toy, and I think much more than my cousins and my brother were. But you know, so I always liked the idea of like getting a scientific principle to turn it into something that you can kind of relate to. I was also interested in coding. You code up like simple games and things like that, even though I got very much sort of, I wouldn't say distracted, but I got really interested in math. So for a while I was thinking maybe I should do math. So I don't know if there was a very ever clear decision when I was that young. I thought I would be a doctor. Like I did the full spiel of thinking about everything, and changed my mind quite a lot.
I love that so you made this game, this little...
It's really simple.
But what made you want to make this game? Like, did
there
you see
was
it somewhere?
TV show. There was a TV show that this was a part of their... it was a game show, and this was one of the, like, if the kids could pass through, then they would go to the next level.
That's cool.
So that was why I was like, I can do this. I know how it works, and that was what I did. Yeah.
Nice. I think I find a lot of people when they find, like, they have an experience that they have to tinker and build something to kind of give them insight into what that field would be like. So it sounds like in that way, this would have been one of those kinds of experiences for you.
For me, it was the opposite. And I think that's where you would see even in my research that I saw this thing and then I was like, oh, I know these basic principles of how electricity flows. And I bet I could do the same thing. It was the sort of going from the first principle that you learn in your, I don't know, elementary school about the flow of electricity, which at that time was this view of like, you know, I was thinking of it as a liquid that flows. I didn't know enough physics to know all the electrons business or whatever. But take that idea and just turn it into something, you know, kind of demystify something that was more like that. Some people are, I think, the more empirically driven colleagues, the experimentalists, I have seen that they're the opposite. They have a lot of intuition about how to build something, and then they kind of try to reverse engineering the new principles that maybe we might have overlooked or didn't think about.
So I know we're wrapping up on time, so I do want to talk about, like, what are you excited about? Like, what is the future of your research? What are you looking forward to?
Oh, this is a hard question because I'm excited about a lot of things. I joke that it's really fun to be us at this juncture of time. I think for academic research, especially for engineers, it's sort of a rare opportunity when ideas and practice become so close in terms of the life cycle of ideas to real solutions and deployment. So definitely, if you're doing any kind of AI, you're at that juncture. If I started thinking about this question of collecting information to do intelligence or sort of active ML and active AI around 10 years ago, and it was really just an abstract question. It started with my student and I went to a talk about how our eyes move to gather information, to facilitate information gathering. So we're like, oh, we should really understand this problem, and it's very different from, at that time, what people were working on. So we're kind of like looking at what comes next, and sure enough, now we are there where it is possible to look at this, and it's really impacting the way we engineer a system. So I'm really quite excited on all directions. On the application side, is like how we will build better and faster and more optimized engineering systems using these techniques, but also going back and develop ideas as what are the underlying hidden facts that data can be used to recover and discover. So I'm really also interested in that question of sort of cracking what are these fundamental simplifying structures that allow us to do things better than what we thought is doable. So I'm really quite excited about that.
Thank you so much for being here. I really appreciate all that you shared.
Thank you for having me.
Thank you for joining us for another Science Like Me episode.